Okay, so it's time right now. This is the tutorial number 2. In this tutorial, we will be dealing with what? Fluid statics. Now there are two important measures that I hope you pay attention to. The first one is right. Pressure, fluid pressure is a scalar. So what is this? Means why? So if you consider a point inside fluids, the pressure acting on at that point actually is independent of the direction, right? So pressure is a scalar, and we proved this during our meeting. Okay, the second thing is really important is the hydrostatic equation, right? Hydrostatic equation. Okay, so what is it? Static equation, and it tells us the pressure under the pressure at a depth h. Right, so let's do this way. Now, for example, if we have a liquid level here, right, and on the top of this liquid you have air, which is P naught. Then the pressure at a point at the depth h is equal to P naught plus rho g h, right? So interesting. This is really important, which you have to practice using it during this course. Right, and in this tutorial, I will be spending quite some times on, basically most of the times, on how to make use of hydrostatic equation to do calculation. And of course, tutorial hour is always not enough. Right? It's too short, and so I will expect you to finish most of the tutorial question at home, together with the revision things that I'm going to give you later on. Right, now in this tutorial section, I think we have time only to give you some example and then some briefing on how to deal with some more difficult tutorial questions. Okay, so here this is hydrostatic equation, which is very important. Right? So okay, now let's go to our tutorial sheet. Right, the first one. Now, the first one is a pretty easy stuff, right? Well, you are told there is a vacuum gauge reading 30 kilopascal. Now, this is really straightforward. Well, I think you, in our first meeting, you have P, the pressure, absolute pressure, or equal to pressure, atmospheric pressure plus the gauge pressure. Okay, gauge pressure, right? Now, this time, now the only thing that you may not know is the vacuum gauge. Okay, now vacuum gauge actually gives you a value which is below the atmospheric pressure, right? So a reading of 30 kilopascal means we have a pressure which is 30 kilopascal less than atmospheric pressure. So the absolute pressure in tanks would be, now atmospheric pressure is given, right? 89, and this time we have a minus, right? Because this is a vacuum gauge reading. So remember, right? Here, pay attention. If this is the ordinary gauge, then yeah, we use plus here. But if this is a vacuum gauge, the vacuum gauge gives you a pressure which is at some value below the atmospheric pressure. So this time, negative sign is needed. Okay, so what you end up is the pressure equal to 68 kilopascal. Right? Now, this question is not difficult, but the only thing is vacuum gauge. Remember, vacuum gauge always give you a value showing how much the pressure is below atmospheric pressure. So remember, negative. Right, so we go back to our main business. Right, the second example. Well, quickly. Now we have balance, right? A pitch here, which is basically a U-tube, right? A U-tube, and on one side you have the rim of a smaller cross-section area, and here the other rim is big, right? And they are in equilibrium. So their equilibrium means that point A and point B are at the same level. Now you are asked to use of the Pascal Law, which basically is hydrostatic equations. Okay. Now the Pascal Law says that the pressure of a liquid is the same if at a particular step is fixed, right? So the pressure at this point, the pressure at point A and B, why they are in equilibrium, and therefore pressure at A equal to pressure at B. Okay, so first one, calculate the pressure at B. Why pressure wow. The pressure equal to force divided by area. Right? Okay, the force is 8 kilogram times G, which is the weight of this waste, right? Divided by 16 square centimeter. So assuming G, where's my pen? Take right G equal to 10 meter for simplicity. Right, for simplicity we take G equal to 10 meter per second square. So pressure equal to 80 divided by 16. So pressure at B, pressure at B equal to 60 divided by 16, which is 5 Newton per square centimeter. Right, and we understand by Pascal law why the pressure of a fluid at a fixed step is constant. So PA equal to PB, again PA equal to PB, so PA equal to 5 Newton per square centimeter again. Fine, right? Nice. Next, now we look at free. Okay, free. Now, what is this weight of these vegetables? Okay, now we notice that we have PA, right? PA, which is equal to force divided by area, and therefore the weight of the vegetable is A times PA. Okay, so very straightforward. It is equal to area is 166 centimeter square, and the pressure is 5 Newton. Right? So altogether, you are having the weight of the vegetable is 8,000 Newton, which is 8 kilo Newton. So no big deal, right? So very simple, and I don't think you have any problem. Yes, should not have any problem. Okay, so Pascal law is basically a P of our hydrostatic equation. No problem, I think. Now we have a manometer. I'm not going to do every example, but I just here to show you some key example, some key messages, and then we go to some other more difficult tutorial, and I will expect you to finish all this at home. Right? Of course, I will give you all the answers 1 or 2 weeks later. I give you some time to finish the tutorials. Okay. And now, manometer is used to measure pressure differential. Right? Well, in this example, you are given the density of these fluids, all right, the fluid in the U tube, in the manometer, and you are told that the pressure gauge reading is 680 kilopascal. But that is the pressure at A, y is equal to the atmospheric pressure plus 80 kilopascal. You are required to find out what H2 is. And you have mercury. And the density of this fluid is this. Oh, a hydrostatic equation. Well, we need to find somewhere to set up our pressure balance. So now usually, because mercury is at rest, it's in equilibrium, so we choose this level, right? B, C, to set up our pressure balance. This is point C. Point C is here. What is this? Point C is here. And by hydrostatic, no, not hydrostatic, but because of equilibrium, the pressure at B equal to pressure at C. Right. Now remember, right, the two rim of the U tube has same cross-section area, so this time pressure equal to pressure. 1. Okay. So next, what is PP? Right, PP. Now this time we apply our hydrostatic equation. PP actually equal to PA, which is the pressure at here. Right, PA. The pressure at this point, which is the same as the pressure in the gas tank, and then plus a column, plus the pressure created by the gas column. Okay, this is the gas here, gas, right, GH1. Okay, gas. Here is a gas column. Now, the density of gas is very small when compared to the mercury. When compared to that of mercury, so the effect of this density, gas density, is very small. Now on the right hand side, we have PC equal to atmospheric pressure because the rim is open to atmospheric pressure. So this is something like that, right? Atmospheric pressure plus the density of Hg mercury, GH2. And these two things are equal, right? So far so good. We have set up this, and next, now the density, we understand the density of mercury is so much higher than the density of the gas. That's the gas, and therefore the effect of the gas density can be ignored. Oh, in this case, PP equal to PA approximately, right? And then equal to PC equal to P atmospheric pressure plus rho mercury GH2. So next one we will have is PA minus P atmospheric pressure equal to rho GH2. Now you are told that the gauge pressure of the gas in tank A is 80 kilopascal. So over here you have 80 kilopascal. And then and then H2 equal to density of mercury, 80 kilopascal, 1, 2, 3, divided by the density of mercury, and then the acceleration due to gravity. Now you may ask, why when we will use g equal to 9.1 and when we are going to take g equal to 10 meter per second square? Now in the future assessment, test, examination, if we will give you, this is a data that we will provide to you. So if the question asks you to take g equal to 9.81, then use the value. Okay. And then the answer is H2 is 0.6 meter. Okay, so now this is the first example of how we use the what was that? The hydrostatic equation, right, to calculate something with manometer. Now the question can be asked in many different ways. Right? For example, you can be given H2 and then calculate back what is the pressure inside the gas tank, right? And also the rim, the right hand side rim can be connected to another tank, right? Having different pressure, and you are required to calculate the pressure differential of the pressure inside the two tanks with a given H2. Now we have plenty of exercise like this in this tutorial. Okay, so I leave those to your home exercise. This actually is the same, but I would like to highlight one important units, right? Here mmHg. So what is mmHg? mmHg is pressure unit. It represents the pressure given by the height of mercury. For example, right, 1 mm mercury equal to the pressure. Now this is a pressure unit. So 1 mm mercury equal to the pressure created by 1 mm height mercury column. So it is equal to 1 mm. Oops, 1 mm mercury equal to this is height, right? 1 mm, and then G, and then mercury, density of mercury, right? So you can calculate what is the Newton per square meter represented by 1 millimeter mercury. So far, so what if you want to given you understand this mm mercury, then you can do this calculation. Now here you have a unit called pound per square inch, which is a British pressure unit. So no matter which unit you are using, remember to stick to the unit, right? But in our test, of course, in our examination, we are using SI unit all the time. Tutorial, we are allowed to use other units, and I think it is good to have to deal with more different unit system, so that you can have a more knowledge about how these things are, right? Okay, so I leave it to you. Next, right here, I would like to do this example very quickly. This is about buoyancy force. Now remember the force. Here we have oil here, which is a substance anyway, right? and its weight is 1.5 Newton in air, and its will weight 1.1 Newton when it is submerged in water. So in air and in water, the because of force, buoyancy force, why the weight of the object it can be different. Yeah. Or the weight difference. Okay. So what is the upward force? When we have a object, right? It has its own mass. Mass is constant, right? So this mg downward force is always constant. But if you this thing, when it is put into fluids, it dissipates fluids. So the buoyancy, which is the force due to buoyancy, F is equal to the density of the fluids, not the ore, right? The density of the fluids multiplied by G multiplied the volume of your object. This is the upward force. So the weight of the object become something like this. Now for air we assume in air, but F is very small, right? So we will be W equal to what's happening? W in air, W equal to mg equal to 1.5 Newton. So now in water, in water the weight is mg minus upward force, right, which is 1.1. Okay, this is given 1.1 Newton is the object, right, weight when it is in water. So mg, the force, the upward is basically 1.5 minus 1.1 equal to 0.4 Newton. Okay, but we understand that this upward force is density times G times the volume of the ore. Right. So very quickly, mol G, wall density, volume equal to 0.4. So the volume is 0.4 divided by 1,000, which is the density of water. And then you have 9.81 here. And you're having a really, really small volume of 0.0000408, something like this, cubic. And which is 40.8 cubic centimeter. All right. So far, very nice, huh? And now, what is the specific gravity? Next, specific gravity. So what is specific gravity? Specific gravity is specific gravity. Specific gravity. Specific gravity is the density of the ore, right, divided by the density of water. Density of ore is the mass, right? Mass divided by volume, right? So the mass is the weight 1.5 divided by G, right? Divided by the 40.8 cubic centimeter. which is when you do the calculator. I did calculator 1.5 divided by 9.81 divided by this 40 something else. So its density is around 3,074 something like that. Kilogram per cubic meter, which is approximately 3.75 that of water. So specific gravity equal to specific gravity which is all divided by density of water 3747 something like that divided by 1000, so it's approximately 3.75, right? The density of oil is about 3.75 times that of water. Okay, so now this is buoyancy. Buoyancy force equal to the weight of liquid displaced or weight of fluid displaced in air, because the density of air is so small, so we usually ignore that ignore the effect of the air density, right? Of course, if you are asked to take in, if this is two fluids, then we have to take in the fluids, the density of the two fluids as well when calculate the volume of the ore or the object, submerged object. Okay, now next we are going to deal with two really involved questions. So before going into it, any questions so far? Oh, you're quiet. We're having I think we still have the windstorm amber warning at the moment. Okay, so no questions. Then we go down. Right, this is an easy question, so I leave it to you. Why? And I will go back to this one later on. Now this is just the inverted U-tube. So what you have to do is to follow hydrostatic equation, and we have just one pressure P here. So this column is P plus rho G, this H, right? And then this column is rho G plus something else, right? Okay, and follow the rules, and you can calculate the pressure differential. So I leave it to you. Okay, I also leave this to you, right? YouTube, against you simple application of hydrostatic equation. So your homework, and this one your homework as well. Now, okay, we go to the dam. We go to the water vessel business. Right, now this, you found this kind of device in a building, in the water tank of a building, and also usually you also found this in the vessel bar. Right, this device, which consists of a door. Right, the H is the hinge, so this door. You can rotate the door in this direction. So now you understand, when we increase H, then the pressure force, right? The pressure on the inside, I suppose, right? On the water side of the door will increase, and then eventually the force is too high, and moment of the force, right, at A can overcome the moment, the kind of anti-clockwise moment of the weight of the door in that case, this door will then rotate outwards. And what happens is when it rotates, the water come out. So the height of the water can be maintained. This happen in, you can see some similar device in water dam, in buildings. Okay, now what this question is about? Okay, now this question is it tell you all this, right? You have a door which is 120 cm wide. The length of this thing is 90 centimeter, and the weight of the door, you can assume the CG is at this point, right? So the weight is acting at the CG, and the CG is 30 centimeter away from A. So you can calculate the anti-clockwise moment created by the weight, right? So now in normal situation, right, if the force acting on this plane is not enough to lift up the door, you have a reaction force here. So you have, in that case, you keep everything, the force balance, the moment balance, the moment at A balance. Okay. However, when time comes, when H is at the now you are required to find the height of the water edge on the inside of the door, like this edge, or this edge. And what is this, right? At this edge, the door is just open. Okay, at this edge, R equals 0. When R equals 0, then it means this door is going to be lift up. And the moment of the water pressure at point A equal to the moment of the weight at point A. Now this is our principle. We are working on this principle to estimate the H. Now of course it's not so easy. So let's look at how we're going to deal with it. Well, we of course we would like to consider a really small area against we will be using some calculus here to do this. Okay, now suppose we have at a distance x from A. Now, because we are going to balance the moment, so moment is the things that we will consider. At a distance x from A, we have a very small width delta x. Okay, and on this x, we have a delta F. We have a small force at that location. Now this small force is of course equal to the pressure at x, right, multiplied to the width of the door, which is W. Well, here is the width 120, and then multiplied to delta x. Okay, right? So, and then the moment of this force at A is x delta F. So you have, which is equal to this. So what is the total moment? Yes, the total moment of course is found by integrating. So the total moment is, right, the total, now the water force is creating an clockwise moment. Okay, so total clockwise moment. Okay, total clockwise movement. Now M, right, total movement, which is summation of this M. And it is M equal to integration of I. Integration of px x w delta x from x equal to 0 to 90. Of course, we just use a L to represent 90 degree, so 90. So what we going to do is to find px, right? So m equal to 0 integrate to L, which equal to L equal to 90 cm, right? Pressure x, W, x, dx. So what is pressure x? Hydrostatic equation, right? Now, we have atmospheric pressure at this point, right? We have atmospheric pressure on the other side of the door. So in this case, we just need to take into account the gauge pressure. So the atmospheric pressure can be negated because its effect will be cancelled when we do the moment balance. Okay. So this time we just can ignore atmospheric pressure, right? Because it's going to be cancelled. Its effect is going to be cancelled when we okay. Its effect is going to be cancelled because we consider pressure on the two sides of the door, right? And the atmospheric pressure is always there on the two sides. So they cancel. The pressure on the atmospheric pressure on the two sides, I mean the effects of atmospheric pressure on the two sides of the door cancel each other. So this time we just need to consider the gauge pressure. Now, suppose this is x. Why? So at this point, px equal to volt gh, right? Volt g something else. Volt g. What is the height? We don't know. The height. Now suppose we assume we let the height of point A below the water level be A. Okay, so px, the height we need to consider is this sine 60 degree. A plus cosine, sine. Right? So this is, so you have m equal to, quickly, right? Volt g A plus x sine 60 degree x, and then w dx. Now, everything is known. A is unknown. Right? When you do the integration, the only unknown is A. Now, this is the anti-clockwise moment. So this is the clockwise moment. Anti-clockwise moment. Anti-clockwise moment. Anti-clockwise moment. Equal to, right, which is given. Right, the weight, the anti-clockwise moment is due to the weight of the door, which is acting at point G, and the weight is W, and this perpendicular distance of the weight from point A is 30 cm. So this is the moment, and W is given here. So what you have to do, which I'm not going to show you here because of time limits. Okay, what you need to do next step is to find A. for the case where the anti-clockwise moment equal to the clockwise moment. After you found A, H is pretty simple. H is after that second, right? H equal to height, at which the door will just be open or just be lift up is H plus this 0.9, which is the length of the door, right? Length of, what is the length? It's the length of the door times sine 60 degrees, right? So by this you got H. Well, try this right later on, and before I send you the answer. Okay. Remove. Oh, this is another difficult question that I would like to share with you before before we dismiss. Right. Now will be I will answer your question after I finish this the briefing of this exercise. Right. I'm not going to work out the things, but I would like you to work it out. And we have some typo error here. It doesn't matter. It's just a space, right? And some font which is, yeah. Well, I will finish it later on, right? And now, if you have any question, just type in the chat room. Now, here we have incline manometer. Now remember, right? This incline manometer is two waves. One is here. The other side is, right, is a smaller one. So now when we apply a pressure differential, right, before we apply the pressure differential, P1 is equal to P2, right? Before that, so at that condition we have this reference datum, right? Now this reference datum line is for the case where P1 equal to P2, right? When there's no pressure differential applied to the incline manometer. Now, when we apply a pressure P1 here, and then the fluid will move down by a distance Z1 here, and well, the liquid will then rise up to the rim, right? And what will you see is, what can you measure is Z2. Now here is usually we set this to 0. We set this as so this is the point where you set your reference scale, right? So you measure from when we apply the pressure, you measure this part of the length, and so you have the inclination. So this length, right? This length actually is you read it from the scale. Suppose it's L. So Z2 is known after we apply the pressure, but you don't know this. This one is unknown. And so next, for this kind of questions, then we will use, well, we will hydrostatic. So the pressure balance is to be done at this point, right after our application of the pressure differential. While our pressure balance, we do the pressure balance at this level. Okay, so the principle is this, and we don't know Z1, right? Next, right, you will find P1 equal to P2, which is here also. Right? P2 is also the pressure at this point. My P1 equal to P2. You can see, right, with hydrostatic equation tell us if we have the pressure balance at the red line. I suppose AA. What is A? This is A. So we have AA. The pressure balance tell us P1 equal to P2 plus rho G Z1, Z2. And this is unknown. Z2 is known. So how to find Z1? Now the first thing you need to do here is to write out P1 minus P2, right, which is the delta P equal to rho G Z1 and Z2, and how actually Z1 can be determined. Well, you are given the diameter of this rim, right? You are given the diameter of these things, right? So, and you know that the volume of the liquid in manometer liquid is fixed, right? So the reduction of the volume of the fluid which is being pushed down by this pressure will then go into the inclined rim. So the volume of liquid here, the volume of the liquid here should equal to the volume of the liquid in this extended region of fluids on the inclined rim. Right? So volume conservation. Volume conservation. Fluid volume is fixed. Is fixed. Okay. So fluid goes out from the reservoir here. Large rim will equal to the fluid volume go into the narrow rim. Right? Wow, very difficult to see. Okay, so here we have a principle to relate Z1 and Z2. Now suppose this length is, suppose this length is L. Okay. So the volume of this the volume here, which represent the amount of fluid goes out of the reservoir, y equal to Z1, and then volume, right? Pi d square divided by 4. I suppose this diameter here is big D and diameter of this small rim is small d. It is equal to the amount of liquid go into the rim, the inclined rim, which is this part of this thing, which L pi d square divided by 4. So Z1 d square equal to L d small d square, and L is Z2 divided by, what is that, psi beta, right? D square. So Z1 equal to, wow, Z2 psi beta d square. No. This is Z1. L is this, right? L is this, L d square, and L equal to Z2 psi theta divided by psi theta. So we done, right? So the pressure differential P1. Now this is the first step why we have to do it before we go further into the question, right? So this one equal to now rho G Z be measured. So Z2 1 plus Z1 equal to what's that? Z1 I forgot is this D square big D square sine theta, am I right? Something like this. I hope I haven't made a mistake. Oh, seem not. Alright, so yes, this is now you can measure this one, or you can write or the other way around, right? If you say this is L, if you say this is L, right, which is the length that you measure in the on the income rim, right? So you can write this. This is D square small d as sine theta. Well, oh no. It should be the other way around. It should be D on that big D at the bottom. Oh, why again? So after you have all this delta P, right? Delta P equal to P1 minus P2 equal to rho G L. I suppose this is L, right? Okay, this is L. Suppose this is L. The length of the liquid extended. The length of the increase in length of the liquid in the incline rim, right? So equal to D square, something like that, as a sine theta. Right, this part Z1 equal to D square L, right? You prove it already. Z2 equal to L sine theta. Alright, we have the pressure known to you. So next we look at, you are required to find out the inclination theta, right? The theta, you are required to find out the theta so that this device can measure 3 mm water, a pressure. Now 3 mm water is again a pressure unit, right? And the accuracy is 3%. Okay. So and the area of reading L is 0.5 millimeter. So it means that we have, well, a change in the 0.5 millimeter actually is equivalent to 3% of 3 mm water. Right. So 3 mm water, the delta P, what we are going to measure is 3 mm water, right, which is equal to 3 mm water, 0.001 millimeter density of water, rho GHG. So this is the delta P. Now the area of delta P is area. Now why we have an area? The area is due to the area in reading this, right? So an area of delta L equal to 0.5 millimeter. Well, this is our area. Millimeter is 0.005, right? With the area, and this area will need to an area of 3% delta P, which is 3%, wow, very small, 3% of delta P, so small, 0.001 times the density of water 1000 times G, right? So it's roughly 0.003 G. So go back to our equation. Right, we have a delta P we have maybe we use a whiteboard there because this you have this is better. Okay, let's do this. Delta P equal to rho G. Now rho is the density of this liquid. L, and then we have D squared divided by big D squared plus psi theta, which we are going to find out the value of theta. Right? We are given D and this. So a small change in the delta. So the small change in the area of pressure, delta P, due to change area in the area in the reading of the scale is like that. And this is equal to 0.003 of G. So it's how you calculate. Now you know G, right? So G can be crossed out. Density is given. Well, you have the density of the fluids known to you, right? So G is you cross out G, right? G is not useful. You cancel, and you know D, which is what else? 8 millimeter, right? Big D is 24 millimeter. Delta L is 0.5 millimeter. Or in that case, you can find theta. The theta is 7 point something, I forgot, which is theta. If you do the calculation, theta should be 7 like that. Oh, 7. Just 7 degree, and then I don't know what that 7 degree, something like this. 7 degree 35. I forgot what is degree, and then what's that? 7.6, something like 7.6 degree. Right. Now the key of this example is to find out this equation. Right. This is the key, and you need to understand the conservation of volume, because the fluid inside the manometer is a constant. So any fluid loss for any fluid volume left this vessel far will go into this incline rim, and this is how you find out this unknown Z1. Okay, so this is what you are expected to be able to do. Now there are other examples which I haven't given you in my tutorial. There are cases where the rim of the U-tube can have different diameter. Right? In some cases, this kind of different diameter, or even on the one rim, you have section of different diameter. Well, this kind of setup usually is used to increase the accuracy of your manometer. Okay, so I think that's it. So any questions? So far the class is really quiet. So any questions so far? Now remember hydrostatic equation, right? Rho the pressure equal to rho GH plus the constant, and if the constant is applied, can be applied to if the constant is not useful, such as what you have what you have seen in the previous example, then pressure equal to only the gauge pressure is useful. And in this case, now in tutorial 2.13, we are talking about pressure differential. Therefore, atmospheric pressure is also not useful. Right? We don't need to actually use the absolute pressure. We can use gauge pressure differential to finish all the calculation. Okay. So will you tell us the solution for the last tutorial rotating this? Yes, right. Actually, all these sort of solutions are ready. But I would just like to give you some time, right? some of you may not have finished, so I say within 2 weeks time I will be giving you a solution, and all the solutions for this tutorial are also available. So do you, Jonathan, have you can you arrive at the answer? Have you tried doing that, rotating this problem? And not yet. Okay, try it. The answer is 7.44 Newton meter. Correct. Now you need to practice more. And there are past you know there are past paper. You can get past paper from the library. You cannot get the answer. And we have also video showing you the solution of the video, showing you the steps and the approach of approach to solve some of the exam questions. But of course, I'm not going to give you now. When time comes, I will give you the link. We have 6 example on previous on the solution of previous exam questions. Where should I integrate? At torque or force? Which one? Oh, the rotation this one is you integrate the torque, because you are asked to find out the torque, so you find the torque equation and then integrate from R equal to 0 to the radius, the outer radius of the disc. Right, and here I would like to take this opportunity to invite you to participate in our fluid mechanics semester start survey. I hope that you can help us to keep track on our teaching, and later on we will have another exercise so that we can have a comparison between semester start and semester end. The result will be used in refining our approach. This subject is